Hello everyone, welcome to Data Science with Partha. In today's video, we will see how to do linear regression with Python. So for the data set, we are going to use the diamonds data set of the Seaborn library. And the task that we are going to achieve today is we'll try and predict the price of the diamonds based on the attributes that are given in the data set. So this video will be a exploration of a typical regression problem. So let's start. First thing that we would want is we need to open pycharm, and this time what I'm going to do is I'm going to take the help of Jupyter notebooks to solve this task. So in our terminal we can type out Jupyter notebook, and as soon as we click enter, Python should spin up a new Jupyter notebook for us. So here, to create a new notebook, all we need to do is click on new and click on Python 3. Now let's give our notebook a title. So I'm going to give this linear regression. So I'm going to just type linear reg for short. And let's also increase the font size. Now, generally speaking, the first step of any regression or classification problem is we need to import all our required libraries. So let's do that. And the libraries can be of different groups. So we are going to import the specific libraries in certain groups. So let's say the first group of libraries that I want to import is the EDA libraries, or short for exploratory data analysis. And the general libraries that are needed for EDA are: first is NumPy, next let's import pandas, next let's import Seaborn, from which we are going to take our data set. Finally, I'm going to import matplotlib. Now, the second set of libraries that I need is the models from Sklearn. Now, since this video is about linear regression, this is the only set of models that I need from Sklearn. So let's just label this as models from Sklearn, and here we have from Sklearn dot linear models import linear regression. Now, the next thing I need is we have to divide our data into certain parts. So generally speaking, the way machine learning works is you will not use the complete data set for building your model. You would actually keep a certain portion of your data for testing, just to see how good the model has performed. So for that, we are going to take from Sklearn dot model selection we are going to import the train test split. Finally, let's also take in our evaluation metrics. So like I mentioned, when you create a model, you also want to see how good the model is performing on your test data. And to check how good the model is performing, we need the evaluation metrics. So there are certain evaluation metrics which are pretty popular for our regression as well as classification problems. So today we'll focus only on our regression metrics. So we can start something like this. We'll say from sklearn dot metrics, import the R scored value, next let's import the mean absolute error and the mean squared error. Finally, just to make sure that the models are actually performing well, we want the cross-validation scores. So we'll say from sklearn dot model selection, import cross-val score. Okay, now let's run this. Okay, so we have to make certain changes here. This should have been underscore. Now because we are actually importing all these libraries together, it could take some time. So now we see that there is a number and all these libraries are imported. So okay, this is silly error. I forgot L over here. So sklearn. Alright. So now that we have the models imported, second most important step that we need is we need to load the data in our environment. So let's actually write it down. I'm going to call the data as df, short for DataFrame, and from cborn we are going to take the load data set function, and here you have to only pass in the data as form of a string. So like I mentioned previously, we are going to use the diamonds data set, so I'm just going to mention diamonds and we are going to run this. So now we see that from cborn the diamonds dataset has been loaded into our environment. And to check whether everything is right, or let's say you're curious to see the first 5 entries or the data itself. To check the first 5 entries, we can use the .head method. So by default, the .head method is going to give you the first 5 entries. Now if I wanted to have a look at more number of entries, so let's say I wanted to look at 10 entries, all we had to do is pass the number in here, and Python is going to give us those number of entries. So here we can see we have columns like caret, the cut, color, clarity, depth, table, price, and some XYZ parameters. And this particular column price, that's going to be our target variable. That is what we are trying to predict given the rest of the information in our data. Now, first step after this is we have to check the overall information just to make sure that the data is complete and we are not missing out on any kind of information. So to do that, we can run the info method. So we'll say df.info, and now we get this nice little table which tells us what all entries we have, and non-null count will actually tell us if anything is missing or not. So if there was some value which is missing, you wouldn't see the number exactly equal to this value. The other way we can check if we have any kind of null values in the data is to go for something like, you can go for the isNA method, and to this let's also add in the sum method. So I'm going to just sum all the values. If there is some kind of a blank entry in there, then it's going to count those values and give me a total number. So as soon as we run this, we see that all the entries are 0, meaning that there is no null value in our data. Now, to get a statistical description of our data, the next most important command is the .describe method. So when we say df.describe and we run this, now you can see that what Python is doing is it's going to give us the basic description about all the numerical columns. So if we take a look at it, these particular categorical columns, cut, color, clarity, these are not present in the .describe method. Only the numerical columns are present in the .describe method. Now if you want a description about the strings or the categorical columns, then there is one small change that we have to do to the above code. So we can write df.describe, and to this we have to mention the include parameter, and inside the include parameter I have to mention that I like to see the objects. So here if we take a look at our info method, you can see that these are termed as categories. So here if I take this and if I run, okay, so no objects to concatenate. So here we have to mention it as categories. And as soon as I mention it as category, it is going to give me another table which is giving the description of those three strings or the strings columns. Here there are a couple of things that we have to take note of. First thing is, when we see top and we see a value, it is referring to which class has the highest number of records or which is having the most highest frequency. So the other way we can check this is if we use the value counts method. So let's take the help of let's take cut as an example and check this. So we'll say df.cut and we'll say value counts. Value count. Okay, and we can see that ideal is having the maximum frequency 21551. That is what is mentioned over here. Similarly, we can check for the color and clarity columns if we want, using the value counts method, and see what is the distribution of this particular column. Now, these particular columns, the cut, color, clarity, all of them are what we call as strings. So here we can see that caret xyz are all numbers, whereas cut color clarity is having some kind of string in here. So if we wanted, we can convert all the columns into numeric values using the one-hot encoding. So one-hot encoding will make sure that all the numbers, all the columns are converted into numbers. And there's one other little trick that we can use for converting the data into one-hot encoding. In pandas, we have a function called as getDummies, which takes care of the one-hot encoding. So let's see this. So I'm going to call this as dummies, and we'll say pd dot getDummies. In this, let's pass in our columns. So here I'm just going to pass in those 3 columns. So we'll say cut, color, and the third is the clarity. Now, one important thing that I'm going to do here is we are also going to pass in the parameter called drop first. So we'll say drop first is equal to true. Now what is drop first is equal to true? So let's take the cut column. So we have these options: ideal, premium, very good, good, fair. Now one-hot encoding, the way it operates is wherever you have this value of ideal, so let's say these are the options that we have, it's going to convert all of these into different columns. So you would have something like cut underscore ideal, cut underscore premium, cut underscore very good, and so on. And wherever the value is ideal, it's going to give the value 1, and the remaining values in that row will be 0. So let me first run this so that you get an idea of what exactly I'm talking about. So now if I ask on dummies, and if I run this, so this is what I was just talking about. So you have these columns: cut underscore premium, cut underscore very good, and so on. Here what you would observe is that cut underscore ideal is not mentioned. Okay. And this is because we mentioned drop first is equal to true. The reason why I've mentioned drop first is equal to true is by doing so we would avoid the multicollinearity issue. So multicollinearity comes in when 2 or more columns are present, and if we have a third column which gives in the exact same kind of information as the other 2 columns, that is when multicollinearity issue comes in. So to take a very simple example, let's say we have columns A, B, and C. Okay. Now if we say that the first value was A, then we would mention that particular column as 1, and the remaining 2 will be 0. So now when we actually remove that particular column A, B and C will be only present. That will also give us the exact same information. So if let's say B and C both give us the value 0, we know that the column value was 1, even though the column A is not present. So even if we say drop first is equal to true, we would get that information. So for example, let's see here the first entry is ideal. Okay, that means if we had converted into one-hot encoding, our cut underscore idea will have the value 1, whereas all other columns will have the value 0. Now take a look at this particular column. So when we said drop first is equal to true, we see that the values under cut premium, cut very good, good, and fair, all the values are 0. that only means that the value was ideal, which was dropped. Okay, so that is where we actually need this drop underscore first is equal to true, so that the multicollinearity issue can be avoided. Now, the next important thing I'm going to do is we are going to attach this information to the actual information that we have. So before that, I'm going to create a new variable. I'm going to call this df underscore small, and we'll say df dot drop, and we'll pass in those 3 columns. We'll say cut, color and clarity. And because these 3 are columns, we have to mention axis is equal to 1. And this will make sure that these 3 columns are dropped. So just to cross check, I'm going to write df underscore small dot info. Now you can see that these 3 columns, cut, color, clarity, are not present in this particular data frame. And the next important step that I'm going to take is, let's add in our dummies columns into this particular data frame. So I'm going to call this df expanded, and using pandas we can concatenate the information. So pd.concat is going to help us to achieve this task. We'll say df underscore small and dummies. Similarly, we have to say it's along the axis, so we'll say axis is equal to 1, and we can cross check. We'll say df dot expanded. Now you can see that this information has been attached to the actual information which was present. Now the next most important step that we can do before actually doing any kind of modeling is we need to understand the data even better. And to do so, the most important task that we have is we need to plot. So what I had mentioned was the EDA, the exploratory data analysis. We need to understand the data using EDA. So let's actually give it a title like that. Let's say EDA. And the first thing I'm going to do is let's try out a pair plot from Seaborn. And I'm going to pass in the actual data frame. So here I'll just pass in df. You'll understand, by looking at the output, you'll understand why I've passed in df. Here we can see that after all this concatenation, the number of columns that we have has increased to a very big size. Now we have 24 columns. So because pair plot takes in a lot of information and it shows all the plots at one go, that's the reason we have taken df. Now out of all these plots, the one I'm interested in is, because price is our target variable, I'm going to look at price, and I'm going to look at all the other charts in here. We can clearly see that along with price, here we have some kind of a linear, not exactly linear per se, but there is some growth along this axis. So this is the caret. So if the caret of the diamond keeps increasing, the price also keeps increasing. So let's look at this information in a little better manner. So let's say for the caret versus price, let's create a different scatter plot, and this time I'm going to increase the size of the plot. So we'll say plt.figure and we'll mention fixed size. So we can give any kind of number. I'm just choosing 10,8. So based on the number, the chart size is going to increase. And we'll go for a scatter plot from Seaborn. We'll say the x-axis is going to be, let's keep it as caret, and the y-axis is our target variable, so I'm going to keep y as price. Now because we have just passed in the column names, you have to also pass in the data parameter. So in our case, data is df. One other thing you might have noticed is when I was creating this chart, we are getting this kind of an output, which actually is telling us which memory location is this pair plot in. Suppose I don't want that, the easiest thing that we can do is pass in a semicolon at the end. Now let's run these two commands. So now as you can see, because we gave it a bigger fixed size, automatically the scatter plot was built, and now we have a nice chart which is big enough to understand the points and look at it better. Now the next important thing that I want to do here is I like to see the Pearson's R correlation coefficient on the chart itself, and let's also build in regression plots onto this chart and see what kind of scores we are going to get. So to do that, first let's actually call in stats from the SciPy library. So we'll say from SciPy import stats, and I'm going to define a new function. This function will take in two things. So let's say I'm saying x and y variables, and it returns stats.pearsonr of x and y, but we want the squared value of this, so we'll also mention that. Now that this function is ready, let's also put in our joint plot, or let's do it in the next line. So we'll say SNS joint plot, and here let's mention x is equal to caret, y is equal to price, and data is equal to df. Along with this, the other parameter that we are going to pass in is the kind parameter. So because we want a regression kind of a plot, we can just pass in kind is equal to reg, short for regression. And one other thing that I'm going to do here is we could actually run this plot, but since we actually want to look at the R-scored value and we have created this user-defined function, let's use that function. So let's say I create a new variable called a, in which I'm saying R2, and we'll pass in our columns. We'll say df of caret, comma df of price, and finally we'll also mention this. Now the variable a will be having the R-scored value stored in. So let's print it out. We'll say I'm taking the help of f strings here, and we'll simply mention r squared value is, and to this we'll just pass in some curly braces in which we'll mention, let's say, a times 100. And since we know it is going to show us a lot of decimals, let's restrict the number of decimals. So here I'll just mention 0.3f, so it's going to give me only 3 decimals. And let's also give a percentage sign on to this. Okay, so let's run this. This should work. Okay, nice. So we get this R squared value is 84.933% because we had mentioned 3 decimals. It's cut off at 3 decimal places. And we also see that Python tried to fit in a straight line in this particular chart of price versus caret. Okay, and the R squared value that we are getting for this kind of a model is 84, or let's round it off to 85%. The next most important thing that we need to do is we have to see what is the correlation between the different attributes. So let's do that. So we'll say, let's give a heading. Because our data has too many columns, I'm going to take the df column and let's pass in the corr, short for the correlation. And if I run this, we should get a table format or a matrix of numbers for the multiple columns that we have. On the diagonal, it is the same column, so we will get ones on the diagonal because the same column is being compared, or the column is being compared to itself. Now to visualize this a little better, what we can do is we can plot a heat map which will actually give us the data in a much more visual format and can help us understand the data in a much easier way. So let's actually increase the figure size this time. So we'll say plt.figure, and let's keep the fix size to something like 15,10 this time. And on top of this, let's mention the Seaborn's heat map. So sns.heatmap, in which we'll just pass in df.corr. And we also want to look at these numbers. So I'll just also pass in the annotate parameter and set it to true. Now let's run this. So we get this nice tabular format, and looking at the bar, we can easily say that if our values are going towards the whitish part and not the dark ones, or let's say the light colored area is the one we are interested in. So we can look at the price, and here we see that price has a correlation of 0.92 or 92% with caret. Similarly, the correlation with XYZ is also very high. Okay. The other thing we can try and do is, because we have actually converted the numbers, the other columns into numbers. So if you remember, we had converted the data and we kept it as df expanded. We can try doing the exact same thing on df expanded. So let's just this time let's just copy the information, and because we have more number of columns, I'm going to increase the fixed size. So let's say the fixed size this time I'm going to keep it as 25,15, and instead of df, let's pass in df expanded, and let's run this. Okay, so as you can see, if we have more number of columns, we should actually give it even better space so that our values are not very small. But looking at this information, we can clearly see that this particular region is having the highest value. So even though we had converted these into numbers, still it is of a very weak significance compared to the price column. So the price row is over here, and we still have the caret XYZ columns are the ones which is giving some kind of importance to the price, and it will be useful to determine the price column. But there's one other thing that you should actually look at this, and it should make you very curious. If you look at the XYZ columns, all the columns XYZ, it has a very high correlation with price, but XYZ also has very good correlation among themselves. So if we look at X, it is highly correlated with Y and Z, almost 97%. Similarly, Y, we have 97 and 95. Okay, so what we are going to do is let's actually drop the X column and create our model from caret Y and Z columns. It's the same logic. We don't want multicollinearity issue to come up. Already X, Y and Z, if I take the X column, 97% of Y and Z is being captured by X. So this time let's actually drop that particular column. And the other way we can look at it separately, we can simply say df of those three particular columns to look at the numbers. So we'll say X, Y and Z, and on this I'll just pass in the chord method, so we can see this thing again. So X is having almost 97% with Y and Z, whereas here we have 97 and 95%. So let's drop the X column and try and create our model and see what kind of results we are getting. So to build the model, we, like I mentioned, we have to split the data into train and test. So that is going to be the next part. So here we'll just mention, let's say I'm just saying selecting data and splitting into train and test. Okay, and here the first thing that we need to do is we have to declare the variables. So we will say x of df, and like we have already selected those three columns, let's take those three columns, caret y and z. Similarly, we have to select the target variable. So we have certain nomenclature that is followed throughout machine learning, that is where whenever we talk about attributes, it is mentioned with capital X, whereas the target variable is also always mentioned in small y. So that's one kind of nomenclature that you will see throughout machine learning. Wherever you find some machine learning code, if you open up that particular code, you would see this kind of a nomenclature being followed. So we have x and y, and we have the dot shape just to check how much data we have. So let's say dot shape of x, and we'll say y dot shape, just to check how much information we have. So we can see that we have about 53,940. That's the complete data that we have. Now we want to split this information into, let's say, let's take 80-20 split. Okay. The general splits that are taken for machine learning are something like 80-20, 70-30, 60-40. That's the kind of ratio people take for creating the models. So when I say 80-20 split, I'm talking about 80% of the data is going towards training and 20% of the data is going towards testing. Okay. So here we can see how much information we could have. So we'll just calculate this. So we'll say this multiplied by 0.2, and let's run this. So about 10,000 or 11,000 rows are going into the testing data, and the remaining data is for training. And Sklearn has a really good function called the twin test split. Inside the twin test split, we are going to take the help of twin test split and convert our data. So there will be 4 parts. Okay, so here we would have x train. The next part would be x test. Next we have y train and y test. This would be equal to our train test split. And in train test split, we have about 2 or 3 things that we need to pass in. First is our x and y values. That's the complete data. Next thing is our, so let's write it in the next line. So next thing is our test size. How much of the portion do we want to give to the test? So like we decided, it's going to be 20%. So we can simply say 0.2. So 20% of the test size will automatically tell Python that 80% has to go into training. And finally, for replication, what we can do is we can declare a random state. And let's take the random state as a default 42. And now let's run this. Now as soon as you run this, your data has been split into training and testing. And we can cross-check this information by checking our xtrain.shape, xtest.shape, ytrain.shape, and ytest.shape. Let's check the numbers for this data. So 53,000 entries have been split into, say, 43 and 10,000. So train test split has done its job. Now the main step, or the most fun part, is the model building. And let's give it a title of its own. And the first thing that we need to do in model building is we need to create a object for our model. So here what we can do is we create a object, and the way we are going to create is we are going to give it a name. So this time I'm going to call it model. So we'll say model is equal to linear regression, linear and we're going to call the linear regression function here. The next most important step is to fit our training data. So we have to give the model the training data. So we'll say fit training data. So the train test split has given us both training and testing data. So the training data xtrain and ytrain is what we need to give to the model right now for it to learn some kind of a equation. So we'll say model.fit and we'll pass in our xtrain and ytrain. Okay. Now once we run this, once the dot fit is executed, so because we only have about 40,000 entries, this got executed pretty fast. So generally if you have more data, what will happen is the dot fit method is going to take more time. But once the dot fit gets executed, what we can generally do is we can test the metrics and see if we are getting a very good value. That means we can see how good the model is. Okay. So the first thing that you can do is something like we can say model.score and we can pass in our test data. We can say xtest, ytest. And when we run this, the model score is giving you the r-scored value. So for regression, the default scoring method is the r-scored value. And we are getting 85.36% overall using these columns. So this data that we have taken, caret, y and z, just by using these three columns, we can easily get a value of 83% for the price. Okay. Now the next most important thing that you can do is we can create some predictions. Okay, so let's see how we can actually calculate the r-scored value in different ways and the other metrics that we have imported. So first thing is let's create a prediction. So we'll say ypred and this is going to be model.predict, and to this we have to pass in our xtest information. Okay. Now as soon as we get this ypred, the next important step that we can do is you could directly pass it to the R2 score that we have imported. So inside R2 score, we have to pass in two things. We have to pass in our actual y data, that is y test, and the predictions. So ypred. Okay. And if you pass this and run, we would get the exact same information. So default scoring was R2 score. You could get it like this, or you could just pass it to the R2 score function and you get the exact same information. Now sometimes what happens is if we have more number of columns, we would be interested in the adjusted r-scored values rather than the r-scored values. So let's also look at how we can calculate the adjusted r-scored value. So according to formula, we can say 1 minus, and here we'll say 1 minus r. So for getting the r value, let's do one thing. Let's just copy this. 1 minus r2 score, this will give us the r value. This gets multiplied with the length of y minus 1, and it finally gets divided by the len of y minus the number of parameters that we actually have. So we can simply say x dot shape of 1 and minus 1. This would be the formula. If we run this, we would get the adjusted r-scored value. That's about the same, almost the same. We only have the difference coming up after the fourth decimal. Okay. The next important score that we need to calculate is the mean squared error. So we have already imported those, so we can simply say mean squared error, and in this we'll just pass in our y test and y pred. So the mean squared error, we get this particular value for our problem. Now here, one thing that most of the data scientists do is they go for something called as the cross validation. Now what cross validation does is, here while doing a train test split, we got only one set of training data and one set of testing data, and we are getting all of these values. But what cross validation does, it's randomly going to split the data into train and test depending on the number of k that we are providing. So by default, cross validation score is going to split our data into 5 parts, and we can take the mean score value and check what is the result. So let's say, for example, I'm interested in to find out if our mean scored error value is going to be let's say mean scored error is something that I want to find. With this particular split, we are getting this value. Let's go for cross validation and check if we are getting the same kind of result. So we'll say np.mean, and here we'll just mention cross val score. We have to pass in our model, and this time we only have to pass in the complete data. So we'll say model x comma y, and we'll pass in a scoring parameter. The scoring parameter is something that you have to check up what is the key string. So the mean scored value, the key string is negative mean scored error or mean squared error. And now if I run this, we get a mean value for the 5-fold. So if I remove the np.mean over here, so let's copy this. And here if I remove the np.mean, okay, and if I run this, you will see that we have 5 values. So it has split the data into train and test 5 times, where the training and testing data are completely different. And for each of those parts, it has calculated our mean scored values. Okay, so this is a much more rigorous way of checking our data, whether it is good or not. Now, looking at the distribution of residuals, we can easily tell if our model is good or not. So we can simply say sns.distplot, in which we'll pass in our difference. So difference between the predictions and the test value. So we'll say ypred minus our ytest. Okay, and if we run this, we get a nice distribution plot. Here you can see that most of the values are hovering near to 0. Okay, plus or minus 5000 is the range, and this is actually a very good model. Had this been something else, if it was not 0, if it was, let's say, 10,000 or 1 lakh, then we would know that the model is off by that particular value. But most of the points is hovering at 0. That means our model is actually performing really well. So if I want to understand what the equation is, then I need to understand the coefficients and the intercept values. And for calculating the coefficient and intercept, we already have two little attributes for the model parameter. Those are .coef, and the next one is the intercept. So we'll say model dot intercept underscore. So this is actually giving you the information about our model. So how do I understand which coefficient is for which? We can actually pass in a small dictionary and we can figure that out. So we'll say dictionary of, we are going to zip in two things. One is a list of our coefficients. So let me just copy it from here. We'll say list of model coef. The next important thing is our columns itself. So I am going to say x dot columns. Okay, and if I run this, you can see that which coefficient corresponds to which column. So this particular equation is telling me that the model has figured out that the price is equal to 9,300 times the caret minus 165 times the y variable minus 835 times the z variable plus the coefficient, plus the intercept, so plus 393. That's the equation that the model has come up with. So with this, this particular session of linear regression is complete. So in the next session, what we are going to do is let's see how we can improve this model further. Okay, so this is what I have for you guys in this video. Thank you.